this lesson, we're going to determine the probability of not E given the probability of E. In logic, not P is the negative of P, meaning everything but P. So in sets, the complement of E is E prime. So notice here in the diagram, you see everything in the set E is within the white circle. Everything outside of the white circle is your complement of E, and it contains all the elements of the universal set that are not in set E. So in probability, the complement of an event is any event that is not of that event. So the probability of E prime, or the probability of not E, would be 1 minus the probability of that event happening. In other words, all you have to do is take the probability of an event happening. 1 minus the event happening will give you the probability of the event not happening. Again, 1 minus the event happening will give you the probability of it not happening. It will give you that negative. Now, sometimes it's easier to find the probability of an event by calculating its complement or its opposite. For example, the probability that an event will not occur is equal to 1 minus the probability that it will occur, and vice versa. If you want to find the probability that an event will occur, all you have to do is do 1 minus the probability that it will not occur. Let's do an example and we'll see how this makes sense. Find the probability of rolling a 5 or a 6 with a fair die. So on a fair die, you have 6 sides. Each side has the dots from 1 to 6. So that means that there are going to be only just 2 sides with the 5 or the 6. The other 4 sides will not have a 5 or a 6 on it. So the probability of event A rolling a 5 or 6 would be 2 ways that can happen out of the 6, this total size that you have. So you can say that the probability is 2 to 6. And of course, you can reduce the fraction there as 1/3. But for now, I'm just going to leave it that way because what I want to find is the probability of not rolling a 5 or 6. So all we have to do is take that probability of 2, 6. That's the probability of getting a 5 or 6. If you go 1 minus 2, 6, you're going to get the probability of not getting a 5 or 6. So let's go ahead and do that. Now we can rewrite that 1 as having the same denominator as the fraction, and then it'll be easier to combine. You know that any number over itself is 1, so let's write this 1 instead let's write it as a fraction of 6 over 6, because 6 over 6 equals 1. So now it's just much easier to subtract these fractions. So 6 take away 2 is 4 over the common denominator of 6. So the probability of not rolling a 5 or 6, in other words, the complement of A would be 4, 6. And of course, we can go ahead and reduce that fraction as well. Now I want to show you a visual representation of this process of what we just did here. So recall there were only 2 sides out of the 6 that were 5 or 6, and that was your event A. And the 2 sides, 5 or 6. So the complement of that, the opposite, the other sides that are not a 5 or 6, that would be your complement of A, and remember there are 4 other sides, so they were the complement there. And again, you can always find either event or the complement of the event by simply just taking one of the events and then do 1 minus that, and you'll get the opposite of it. And there you have it. Let's do another example using the not. So when a single card is drawn from a standard 52 card deck, what is the probability that it will not be a king? Now we know in a standard deck of cards there are 4 kings because you have the 4 suits. So what is the probability of not getting a king? Well, all we have to do is find the probability of it being a king and then do the 1 minus the fact that it's a king, and you'll get the not a king. So there are 4 out of the 52 cards that are kings. So there you have that probability, and all you have to do is do 1 minus that, and you will get the probability of it not being a king. So we can write the 1 as a fraction 52 over 52. When we subtract that from 4, we get 48 out of 52. So that is the probability then of not getting a king. Now that's just showing you how this method works. Honestly, for a problem like this, it would just be easiest to take your deck of 52 cards, not being a king, subtract these 4 kings from it. Take them out of the deck of cards. And when you take them out of the deck of cards, that's going to leave you with 48 cards out of 52. When you reduce that as a fraction, it reduces to 12/13. Okay, so I just want to show you how this method works. I mean, of course, you can solve it whatever way that works best for you or that makes sense. Now, probability of events involving not. If you're dealing with percentages, so if the probability is expressed as a percent, the probability of the complement of the event can be found by simply subtracting the probability of the event from 100, which is the same as 1. So here's what I mean. The probability that it will rain in Miami today is 20%. So what is the probability that it will not rain? So when you have the percentages and you want to find the not of that event, instead of the 1 minus something, since we're dealing with percents, you're going to say 100 minus 20. And then what you get is your not, and in this case, there's an 80% chance that it will not rain in Miami. Events involving or, the additive law of probability. In this objective, we're going to determine if events are mutually exclusive. We're also going to determine the probability of events involving or using the additive law of probability. Let's first define mutually exclusive. 2 types of probability using or can occur. The event may be mutually exclusive or not mutually exclusive. Events that cannot occur or happen at the same time are called mutually exclusive. In other words, they cannot happen at the same time simultaneously. For example, find the probability of drawing 1 card from the deck and selecting a heart or diamond. Are these 2 events mutually exclusive? In other words, if you take a card from the deck and that one card you take, can it be a heart and a diamond? No, it can't be both. You can't take one card from the deck and it be a heart and a diamond. So therefore, we say that these two events are mutually exclusive, meaning they are independent events. They cannot occur at the same time. Let's do an example. If a single die is rolled, what is the probability of landing on a 2 or an odd number? So the first thing we have to ask ourselves is this a mutually exclusive event? In other words, can you land on a 2 and an odd number at the same time? If you can, then it is not mutually exclusive. If you cannot do that at the same time, then it is mutually exclusive or independent events. So, landing on a 2 or an odd number. Well, is a 2 an odd number? No, 2 is not an odd number. So therefore, the event of rolling a 2 is a totally separate event than obtaining an odd number. On the dice, your odd numbers are 1, 3, and 5, which are totally different from the 2. So therefore, these are two mutually exclusive events. So the first thing you ask yourself about events that involve or is you want to know if it's mutually exclusive, meaning independent events, or not. Since this is mutually exclusive, yes, you're going to use the formula of to find the probability of A or B. All you have to do is add the probability of A and the probability of B together. So let's first find the probability of event A. Event A was of rolling a 2. So there's only one side of a dice that is a 2 out of the 6. So that would be 1 out of 6, 1 over 6. Now let's find the probability of event 2. Event 2 is of rolling an odd number, and as we said, there are 3 sides on a die that is an odd number. So that would be 3 out of the 6. So our first event again of rolling a 1, 1 out of 6, plus the event of rolling an odd is 3 out of the 6. Add them together, add your top, that's going to give you 4. Keep your denominator of 6, that's going to give you 4 6. Once we reduce our fraction, it's going to reduce to 2/3. So the probability of landing on a 2 or an odd number is 2/3. What is the probability of the spinner to the right landing on an even number or a number greater than 5? So we have two different events here. So the first thing we have to do is ask ourselves, are these events mutually exclusive? In other words, are they independent? One has nothing to do with the other. Well, let's see. Landing on an even number. So with the even number, that would be your 2, 4, 6, and your 8. A number that's greater than 5, that doesn't include 5, so that means it would be 6, 7, and 8. Okay? Now, since 2 of those numbers repeated themselves, in other words, 2 of those numbers were in event A, and they were also in event B. So these are what you call not mutually exclusive. Notice here when we drew a Venn diagram, what A and B, set B share in common was the 6 and the 8. So whenever you have events that are not mutually exclusive, meaning they are not separate or independent, there's a different formula for that. Similar, but you're going to attach something to the back. So you're still going to find the add the probability of event A plus add the probability of event B. But then what you're going to do is subtract from that what those 2 events had in common. Okay, so let's go ahead and do that and see what it looks like. So finding the probability of finding a number that is an even number, we had again 2, 4, 6, 8, so that's 1, 2, 3, 4 numbers out of the 8. And then the next event, event B, was getting a number that's greater than 5. So that would be 6, 7, and 8. So that's 3 out of the 8 numbers. And then what these 2 events had in common, that would be that intersection point. There was the 6 and the 8. So that's 2 numbers out of the 8. And when we calculate that, we will have the probability here. So let's just move from left to right. 4 plus 3 is 7, and 7 take away 2 is 5. So then that's 5/8. So the probability of the spinner landing on an even number or a number greater than 5 is 5/8. Let's do one more example. Here we're given sets and we're asked to find the probability of event A or B happening. So here event A is your odd numbers 1, 3, 5, 7, and 9. Event B are the 2 numbers 4 and 8. So would you say that these events are mutually exclusive, meaning they're independent, one has nothing to do with the other, or do they share some common numbers, meaning that they are not mutually exclusive? Well, if you take a look at one, you have all of your odd numbers. The other, you have 4 and 8. And there are no odd numbers that contain 4 or 8. So these 2 events are what we call mutually exclusive. And then all the other numbers, notice, that are in the universal set, they're on the outside. However, just focusing our attention on set A and B, they have nothing in common, so therefore these are 2 mutually exclusive events. So all we have to do is just simply add the probability of event A and then add the probability of event B. So the probability, first of all, let's get our bottom number as far as the total here. We have 10 numbers here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So event A would be 1, 2, 3, 4, 5 out of the 10. Event B will be 2 out of the 10. So 5 out of the 10 plus 2 out of the 10 is going to give us 7 out of the 10. And that is our probability of it being event A or event B. Our next objective is to understand random variables and probability distributions. Probability distributions. A random variable x is a variable whose value is the numerical outcome of a random event. For example, an instructor asks her students how many siblings they have. The results are shown in the table below. Find the probability that a randomly selected student has 2 siblings. Now, in this probability distribution table, the random variable x can equal 0, 1, 2, 3, or 4. So if you look at the table, the value x, where it is equal to 2, is paired with 8 outcomes. There was a total of 27 students surveyed. So the probability then that a randomly selected student will have 2 siblings out of the 27 that are surveyed. So since 8 corresponds to the random variable of 2, and 27 is the total students surveyed, it would be 8 over 27. So therefore, the probability that a randomly selected student has 2 siblings is 8/7 or 29.6%. And you know we get the percent from simply top divided by the bottom, and then move the decimal 2 places to the right and write your percent symbol. So there you have it. Using the same example, find the probability that a randomly selected student has at least 3 siblings. So at least 3, meaning that it could be 3 or more. To write that as an inequality, because that is an inequality statement, the random variable x, we're finding the probability that it will be greater than or equal to 3, meaning it can be greater than 3, and it can also be 3. Now notice here our random variable x goes from 0 to 4, so greater than or equal to 3 would include those people who have 3 siblings as well as 4 siblings. Now if this chart were to go on, it would certainly include those who have greater numbers, but sticking to our chart here, the number that's associated with 3 would be 2, and then the number that's associated with 4 would be 1. So to get the probability of that a randomly selected student has at least 3, you would have to add the 2 plus the 1, and that it would be over your total that was surveyed, which is 27. So 2 plus 1 is going to give you 3, so that'll be 3 over 27, and then when we reduce our fraction, that's going to give us 1/9. So therefore, the probability that a randomly selected student would have at least 3 siblings, top divided by the bottom, turn it to a decimal, and then a percent would be 11.1%. Probabilities associated with every possible value of the random variable x make up what is called the probability distribution for that variable. Here's an example of a probability distribution table and its histogram. So the Probability distributions have the following properties. 1, the probability of each value of x is greater than or equal to 0. 2, the probabilities for all values of x must add up to 1. So if you were to add this column here of these probabilities, it would add up to 1. So that's your proof to show that that distribution is valid. Again, 1 is that for each value of x, the probability is greater than or equal to 0. And then second, the sum of the probabilities is equal to or adds up to 1. Okay, so using that same example, let's see if we can answer the question of what is the probability that a student chosen at random has fewer than 2 siblings? So the terminology of fewer than 2 siblings, that would be an inequality statement of saying, yes, you can have less than 2, but it doesn't include 2. So to write that, you would know you want to know the probability that x is less than 2. It would not include 2, anything that's fewer than 2. So on our chart, if we look at fewer than 2, it would be those who have 0 and 1 siblings, because those are the only 2 numbers that are less than or fewer than 2. So then we take the probabilities that are associated with these. For 0 siblings, it was a 0.037, and for 1 siblings, it was 0.556. All we need to do is add these two together, and we will have the probability of having fewer than 2 siblings. Now be careful, don't try to add up this column and then write that on the bottom as a fraction. That was a totally different table than what you have here. That was a frequency table. And this one is a probability table. So one was a frequency distribution table, and this one, because you have the probabilities already there in your decimal form, this is a probability distribution table. So all you need to do is add the 2 values, and there you have it. It's 0.593, or if you want to write it as a percent, that group will consist of 59.3%.